This is the Amp Hour Podcast, released August 28th, 2017. Episode 357. An interview with Rick Altherr. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Rick Altherr, a Googler and also electronics hobbyist.
Welcome, Rick. I'm glad to have you here.
Thank you.
So you and I met through the meetup in San Francisco, but I think we had followed each other online prior to that. And you said you're a Googler. Maybe we should start there because there's. I think there was a disclaimer in that Googler statement.
Yeah, so I've been at Google for 8 years, and I do work in the platforms group, which designs all of the equipment that goes into data centers. So that includes servers, storage devices, networking equipment, etc. And I think we were going to talk primarily about server equipment, and so there's the disclaimer is I can't talk about work in terms of the
right. And in rack 44, right?
Yeah, specifically, I cannot speak anything authoritatively
Sure.
as Google, but I can certainly cover any sort of, industry trends and things like that.
Well, lucky for you, no one ever speaks authoritatively on the Amp Hour, specifically me and Dave. We have we have no authority over everything. We mostly just make it up as we go along. So, excellent. So the reason I was, you and I had talked obviously before. You gave a great talk about car stuff, and we'll probably get to that at some point here as well. But you first showed up with like a server box under your arm, and I kind of realized I don't know much about okay, so yes, obviously servers are made out of electronics, they're computers, blah, 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 but I don't really know the state of the art. So I was actually really interested to kind of figure out where are we? Like where, what is the normal kind of processor power that's in a server these days? And then what are some of the other challenges that we're kind of facing as the cloud and everything keeps scaling? Yeah.
When I came to HHCG with the Zayas machine, I think a lot of people have this mindset still of 19-inch rack machines, kind of 1U standard stuff. And the world's really changed a lot. That's still very true for traditional enterprise deployments. They deploy in that way. That's what you'll buy from HP or Dell. And you might use that if you're deploying upwards of, tens of thousands of machines. When you start getting into the 50,000 or more machines deployed, you start to realize that you're paying for a lot, especially things like plastics and front panels. And there's a lot of misfeatures that don't make sense. Like, do I really need an LCD panel to tell me the system health for each machine on the front panel of it?
I see.
Entire room full of machines that no one's going to see. So there's just all these different considerations that come into play when you start hitting these extremely large scales.
That's interesting. Yeah, I guess to put that in, so like the 19-inch 1U rack, first off, that's when you say 1U, that's one unit, right? So because you can start to stack them up taller and fit other things in there, right?
The 19-inch standards for rack mount machines, there's a standardized unit. It's 1U. It's roughly 1 3/4 inches. And there's various depths. But basically, it's sort of the mechanical form factor has been set up so that you can buy equipment that's 19-inch compatible and put it into a rack. And so you can mix and match.
Okay.
When you look at the Open Compute project and some of the more what they call hyperscale type deployments, people have moved away from that.
Well, maybe could we step back as well too? So so you're kind of talking about I forget what it's called. Is it colocation? Is that right? Is that what you mean when you say that someone might buy a rack unit off the shelf? Is that what you mean by that?
Well, yes and no. So if you're looking to purchase rack space as an individual, not the company, but physical space.
Just a space and a rack. Yeah, right. Your box goes here, right? That we made that joke before the show. Everybody's Silicon Valley fans out there, right?
Yeah. So when you are going to purchase a rack, space in a rack, at small scale where you're deploying a couple of machines, as an individual or as a small business, you might go to a colocation facility, and basically they sell you effectively space, power, cooling, and networking bandwidth.
It's like an RV hookup, right? You're basically buying an RV hookup. You bring your own RV.
Exactly. You come in and stick your equipment in there. Now, I mean, there's a lot of other ways you can purchase, virtual servers and things like that. But this is when you're actually deploying your own physical equipment.
Right. And I think Dave actually has. Dave couldn't make it. Sorry, I should have said that at the beginning. But I think he actually has that for his forum. I remember him saying something like that. So as a reference.
Yeah, it's a pretty common thing, especially when you get into reasonable size.
Yeah, millions of hits per month kind of thing. And
yeah, because virtual services can get expensive, and some people just like having the ownership aspect of it is my equipment. As you move up a larger, eventually you get to a point where you're buying whole racks from a colocation provider, and then you're buying a cage where you have, it's basically a fenced off area inside the building that you own that space. And then you get to the point where you start questioning, should I just own my own facilities?
Right.
and that's where you're getting into medium to large size enterprise deployments.
Could you give us an idea on like another company that might be like of that scale? I'm going to assume your employer is monstrous, but
well,
just off the charts.
I think you'd be surprised if you think of any large company. They are likely to have their own on-site premises.
Oh, really? Okay.
For IT infrastructure. It's extremely common that if you're a fairly large employer, you would have at least a small IT staff and hundreds of machines in order to run your mail services and development works, back-end services and things like that. So it's extremely common, even for, I would say, on-premises, one or two sites is common even for relatively small companies. When you start getting into many sites and owning large facilities, you start moving up the scale and you get into people like Fidelity, basically like financial. Financial services is one, insurance, basically anybody who has a lot of data processing that has to do, or, those types of back-end applications where they just have a lot of work that needs to happen and a lot of data to be managed. And so they do it all in a data center.
Interesting. And when you say this too, so can we break out the processing versus storage you're talking about as well? So like, does storage still happen in these racks as well, or is that like a different style of thing?
It varies from space to space. So I tend to think of things as there's the traditional enterprise world, the large enterprise world, and the hyperscale world. And they all behave differently in terms of the types of equipment they buy and what they do. So traditional enterprise, you're likely to buy a SAN application or like a NetApp filer or some sort of dedicated storage system that lets you map iSCSI volumes onto individual servers. So every machine has its own boot drive, but you're actually trying to leverage central storage applications with high redundancy.
Got it. And then like really, really fast I/O links to get the data in and out of that as fast as you can, that kind of thing.
Exactly. And depending on what your needs are, you might have a machine that actually has a lot of direct attached storage, like a database server, but often SANs are very common in traditional enterprise. And that could all be in the same rack, or you might move it into different racks. It just sort of depends on what you're trying to do.
Are there any like visualizers online that kind of show like example of how disparate, like if I go to like a shopping page and I'm looking at two pairs of sneakers, right? It's probably that those images are stored relatively in the same area, but it's also possible that they could be cached across the world or something like that, right? So like, are there any like visualizers online for that kind of stuff? Do you know of?
Of where information comes from?
Yeah, just like, where it might end up all going, like even like visualizing inside a data center kind of thing. Are there like...
I'm not aware of any. I mean, the example you're giving of like fetching static images would often get into content distribution networks like Akamai.
Right, Akamai. That's what I think of because they're so fast and just like crazy.
Yeah, and that is one particular deployment model that's a little different. But when you're talking about the actual data flow inside of a data center, I think the big thing to think about is when I talk about traditional enterprise, it's the distinction between that and large enterprise for me is traditional enterprise, you build a server for an application. So this is my database server. This is my Exchange server. This is my web server. And that is its purpose. You install an OS on it and you load all the applications on it and you manage it that way. And if it dies, you lose that application. So, and I mean, that's a traditional way of doing things.
Sure,
that's just how you would manage it.
Right.
And people do things like move to virtualization and run, ESX clusters and things like that to try to give some fault tolerance to it. But it's still this classical model of I installed an OS and that OS runs my application as a single instance. When I think of large enterprise, what I see is people adopting what the hyperscale folks, the cloud providers, have called, scale out architecture. So it's using things like OpenStack and other job scheduling systems to launch an application, and you don't actually care what machine it's running on.
Right. It's just whatever's free, right?
Right. And the advantage is it sort of bin packs across all the machines. So it finds the storage and the network and the processor and RAM that's available in a way that can be used together for your application. And you just get that dynamically allocated to you across whatever resources are available.
And so just to tie it back to the previous example, you said in the past you would have had an OS doing that. So is there some kind of like higher scale thing where it's just raw resources and there's like some monster OS that's doing this resource allocation? Or how does that, when you said RAM, that's the one that actually kind of tweaked my brain. It's like, wait, you can just tell it what RAM, I guess you can tell it what address to do, but then how big is the address space?
Well, so an example of this, there's a variety of scheduling systems, but if you look at Kubernetes is one I'm pretty familiar with. The tech lead happens to be a former manager of mine. And you describe the resources you need. And the whole point is that Kubernetes as a system knows what every single machine provides in the entire cluster. So then you're able to make these requests, and it goes out and figures out, oh, well, this machine has enough CPU and RAM for you to run your job, and you don't need any local storage. So you fit here. So let me just go ahead and launch your application on that machine for you.
Oh, okay. So it is quantized at the machine level then? It's not like taking RAM from machine 1 and processor from machine 7, right? It's just saying, is there enough on this one machine for this one job? And
so most of it is around trying to bin pack at a machine granularity.
Sure. Okay.
Sometimes it isn't. It depends on how sophisticated you get. Storage is one of those things where you can have the concept of local storage, but you also have cluster level storage.
Yep.
So RAM isn't quite at that point yet, but I know that's one area that people would love to see because you often have stranded RAM where I'm out of CPU on this machine, but I have plenty of RAM.
Huh.
If I could give it to somebody else, I would.
Exactly. Pass it out. Yep.
Yeah. So...
But then, doesn't the I/O become a huge thing because you're pushing data in and out between machines then? Or is that...
Of course, which is why you see at the large enterprise and hyperscale, networking development has been at ridiculous pace. 10 years ago, 10 gigabit to a server was unprecedented.
And now they're at 100 gig.
Yeah, exactly.
Yeah.
So it's moved pretty rapidly because you're actually shipping a bunch of data around between all these machines, either in a rack or even across racks within a cluster.
Okay. So it's just about kind of shortest path, but almost on a room scale instead of on a a system scale or a processor scale or whatever, wherever it's going.
Right. Now, the other part of this is a lot of the reason these enterprises are moving toward the scale-out architecture is it's self-healing. When a machine dies, it moves the job somewhere else.
This is going to start sounding creepy, isn't it? It's going to be like, well,
it's mainly a lot of the hyperscalers started to realize that as you get larger and larger number of machines, all of those machine failure statistics that you see, the probability that a component will die, start to become rates of occurrence. You're going to see failure all the time. So instead of trying to design every single component to tolerate failure at an individual level, you tolerate failure at a cluster level.
You just make a fast eject rack where you can just pop the server out and pop a new one in, right?
It's not even about fixing the hardware necessarily, though. If you look at the open compute designs, they are designed for rapidly being removed and ease of
kind of.
Yeah, and just toolless removal, very easy to operate on for repair. But at the software level, you, instead of trying to deal with things at a single machine level of, having RAID arrays and things like that, you bump it up to, when the machine has a problem, you just move the job to a different machine.
And And then if you can use some of the resource, then you could turn that part back on. Is that kind of the idea?
Yeah, and you can decide when you're going to go fix that machine. So I can just over provision by so much, so that repairing machines in these large scale deployments is a constant activity. It's not that you wait for something to fail and then you go fix that. It's every day somebody walks in and there is a queue of, I need to go fix these hundreds of machines.
And when you say fix, you mean just replace, right? Just rip out, do something new, or put something new in, right?
It's going to vary from provider to provider. Often it's actually more beneficial to fix the machine in place. Basically, walk up to the machine, pull it out onto a mobile cart, swap out the couple of components that are bad, put it back in the rack, and walk away.
Interesting. So does that mean that you have a lot of like onboard diagnostics as well then? So you can say, oh, well, I already know machine 58 has the 12-volt rail is looking a little low. I'm going to go change the power supply and then see if I can fix it later on a bench? Or
Yeah, pretty much. I mean, we're never going to actually fix the power supply on a bench. We're going to toss it in a bin and send it back to the manufacturer and tell them it's broken. And let the RMA process sort it out.
Right. That makes sense. Yeah.
But it's a very common thing that if you look at the components in a data center, hard drives and DIMMs fail a lot. I mean, I don't think that'll be a surprise to most people, but so when you see a hard drive fail, you just have somebody go pull that hard drive out and set it aside in the pile of to be sent back to the manufacturer.
Right. Seagate gets a two-ton box of Platins and whatever's, right? Well, I guess full drives probably. Yeah, that's crazy. So specifically for hard drives too, because this is really interesting to me. As you were kind of saying all this stuff too, Dropbox, Google Drive, all these things, all these services that are just living in the background, obviously are helping us out. But I don't think about them on a daily basis. I'm sure you do, but so much stuff is just behind the scenes now that I don't even think about it. But things like that, where you say like a hard drive dies, well, I've lost pictures before. I've lost music before, whatever. But how many redundant copies are there in those? I mean, they're always raid setups, or how does that work?
Actually, nothing in the environments I work in is RAID at all.
Oh, okay. So it's just
it's again that principle of you work at a higher level in the stack. I'm not trying to resolve the problem at a machine level where RAID would apply.
Because that's actually doing bit copying and checking on itself at the bit level. Right.
Instead, what I tried to do is what a lot of providers do is deal with it at the cluster level. So if you look at something like Gluster or the paper on GFS, they discuss a lot of these concepts of you're actually splitting it up and distributing the files across many machines. And you're doing things like either having a set number of replicas, or you're doing Reed-Solomon code, so you can actually recover from a subset of the overall availability. And that's there not only because of hard drive failures where you actually have true data loss, but simply unavailability of a machine. It might be temporarily unavailable because it got restarted.
Or someone else is accessing data when you right when you need to get it, right?
Well, that's more dealt with in terms of a performance issue, and so you get queuing. But it's things like firmware updates. They have to happen.
Oh, sure. Yeah. Okay.
OS updates. Got to happen. Mm-hmm. Even testing the battery on the battery backup to make sure the machine will survive.
Right.
The machine might actually die. That's how you find out the battery's bad. Right.
I mean, this sounds like this rapidly moves towards this sounds like an industrial system where there's planned maintenance, there's unplanned maintenance, there's just,
that's exactly what it is.
Yeah. That's
now,
crazy.
the interesting side effect of that, is if you start thinking about the probabilities, I mentioned you see all these, what you would often think of as occasional failure type things. How often do you see a hard drive fail? At one point I did the calculation and I was seeing a hard drive fail every 5 minutes.
Oh my God. That's a lot of clicks of death.
And it's just that's the nature of having so many devices that the MTBF becomes those rates.
Yeah, right. Which is mean time between failures for people that are not playing along at home, or playing along at home, whatever. That's significant, and that's probably still really good from the manufacturer side of things, right? It's not it's not like they messed it up and they have the untenable MTBF. It's just that there's so much M.
Right. Well, it's when we talk about MTBF and you think of it as mean time between failure, I know I fell into the trap of saying, oh, well, that's the time between failures on a single device. Well, that's not what it is.
No, it's the group, right? Or it's taken in aggregate?
It's the total number of active hours in a population.
Yeah.
The amount of time in a population's working hours that you will see one failure.
Right. It's like saying the average age of death of an American, right? It's not like everybody's going to die at 77 or whatever it is, or every male will die at 77.
Right.
It's that, over time, that's what it's been.
Right. And so if I say I have a 1,000,000 hour MTBF on a hard drive, but I have 1,000,000 hard drives, you start to see the problem of they're on power for 1 hour.
Yeah.
One of them is likely to die. Yeah.
Right. But it could also be 20, right? I mean, that's the other thing is that... Because it's averaging over even more than the 1,000,000, isn't it?
Yeah. I mean, it depends on what your actual population size is. Yeah. But yeah, I mean, those factors become very important. And that's why approaching it as I'm going to wait for things to fail and I'm going to go get that machine back up and running just doesn't work. You just have to have everything assume failure will happen constantly.
Right. Instead of success is assumed, it's failure is assumed.
Pretty much. Yeah. Yeah. At least one level of failure.
Yeah.
And you start getting into things that are incredibly unlikely events becoming plausible.
Such as?
Such as, I often tell people that their product is not done being shipped at work until one of them has actually caught fire in a data center. Because even though it is extremely unlikely that your power converter is going to fail in such a way that it will catch fire, deploy enough of them and it will happen at least once.
Wow. And so that means that you've been on hand with a fire extinguisher? How does that even work?
Well, not me personally, but yeah, there's actually a thread or a forum that records just things that caught fire in data centers. It's just pictures. And you know, it happens on a semi-regular basis, and it's expected. It's really good information when you pick apart why did it happen. And in some cases, you just find it was a one-off manufacturing defect. But that's what you would expect. Yeah.
Interesting. And then is that something that like a team would go in and actually do like a failure analysis on that kind of thing? Or is it like an
usually.
RMA process?
Yeah, especially if it's a fire. If it's just a failure to operate, maybe not until it becomes a consistent problem. Yeah.
That's interesting. So and so when you say your product is not shipped, do you mean like if you're talking to like a software engineer at a hyperscale thing because it has to be on enough machines to have that happen, or you mean the hardware side?
I mean the hardware side. Okay. So I work with a lot of hardware folks. I'm primarily work on firmware and the software side, but we design a lot of equipment at work, and so it's knowing when that hardware is shipped in enough volume that you've actually seen what the failure modes are going to be. Got it.
Yeah. Well, I don't think I've ever shipped enough hardware to have that failure kind of happen, but I guess that's good too. Yeah, man, that's nuts. And so does that mean that, okay, so then designing the hardware, how much planning? So I kind of already alluded to like self-monitoring and stuff like that, and then talking up through the firmware up to the OS, whatever, of like monitoring itself. But how much is there for like UL testing is for like safe failures, right? Not whether or not it gets UL tested, but how much is it like trying to make sure that there's like fire retardancy and stuff like that, if that's a real concern.
So when you're designing your own equipment for your own use, you have to be a little careful with, you need to meet the safety considerations of whatever nation you're shipping into for use. But you get to skip some things because you can assume a lot about the environment. It's a lot like an industrial environment.
Yep.
I have full control over it, so I can make statements of only people who have proper training to deal with this can actually be there.
Oh, I see. So you don't have to like protect the user from themselves because your users are expert users and they're also under your employer's employee kind of thing.
Yeah, and there's a lot of nuance and detail there that is going to vary from company to company. But
yeah, of course.
When you just think of it as the data center is the computer, so you have to think of things at a building scale.
Yeah.
in terms of where does it make sense to do the right type of analysis and regulatory enforcement.
So when you say hyperscale as well, I mean, I can think of some internet giants that would probably fall under that. Do all of them have hardware groups? Is that like a thing?
So I can't say extensively.
Sure. I mean, best guess. That's fine. Yeah.
Well, so I'm heavily involved with the Open Compute Project, which is a group that was started by Facebook back in 2009 or so.
Yeah, I remember when that was announced. I always thought it was just the power supply for something like that, but
no,
it's more.
So they actually do the rack designs, they do servers, networking equipment, and a lot of other companies have joined in. So you actually see things like telco equipment, like passive optical networking. Lots of different technologies are showing up. And
that's great. It's like ad hoc standards pretty much without a standards board. I'm assuming it's like shared knowledge mostly, right?
Yeah, exactly. It's an attempt to drive some standardization between these players that do make their own equipment.
Yeah.
And a lot of it's toward interop and being able to share equipment designs. Because if Google designs their own and Facebook designs their own and Microsoft designs their own, then we're kind of locked in to one path.
Right.
If we can all share, at least at a maybe machine level or rack level, then that helps a little bit in terms of being able to explore different opportunities.
Well, and how much is it? So I would assume that that there's some kind of competitive advantage from designing custom hardware that the other players don't have. But is it like I would also assume that it's more about how much you can deploy at scale versus how much using a slightly better processor than the other person or a slightly better power supply than the other person. It's more about just, can you get it out there? Is that a correct statement?
I think there's two different avenues. There's having a competitive advantage. So where does it make sense for me to invest my specific resources to be better than my competitors?
Yeah.
And where should I be investing to help keep competition going inside the overall marketplace?
Right, because you're also trying to broker deals with all these vendors that are selling you the parts and everything too, right?
Right, and it's really about trying to make sure there are options available and that we're keep the innovation going in terms of new development. I want to see multiple processor vendors trying different things.
Yeah, right.
And that doesn't necessarily happen unless we're all able to be in a space where we can adopt new technologies quickly.
Right. I mean, this is not server based, but I was really surprised about the USB-C thing. It seemed like a lot of tech giants kind of getting together and on an actual standard as well with the USB, working group or whatever it is. But like, that makes a ton of sense. Like, I don't know. I think that these kind of like standards and stuff like that, yes, there are hassles at the beginning, but the dividends in terms of like driving down hardware costs and increasing adoption over time, like that kind of stuff. Like thinking about, again, just to use the USB-C example, then you have 5 different chip vendors making hardware for it, and then that competes with one another, and the connector vendors and everybody,
Right.
And that's just one thing versus an entire server.
Yep, exactly. So through Open Compute, I've gotten to know folks at Facebook and Microsoft, Rackspace, Fidelity, Nokia. There's a whole bunch of these different companies. I would say everybody tends to know the top tier folks. The largest deployments. But there's actually quite a few that fall into this, I think of as large enterprise. They're not trying to be public cloud providers. They're not offering it as a billable service, but they have something that resembles a private cloud.
Got it. Interesting. I mean, I don't know what I was thinking about. Like, I guess I was kind of envisioning like, if you'll excuse it, like, like buying from Dell or something, like just buying the whole rack. So I guess I never really thought about this, but of course, everything you've been saying has made a lot of sense in terms of why would you buy all the other accoutrement? Like you don't need that other stuff. So open it up and get your airflow optimized otherwise.
Yeah. If you look at what a Dell machine offers and its form factor and everything, and then you go look at a Open Compute Leopard machine or a Zayas machine, I mean, you can see there's night and day difference of there's like a U-shaped piece of sheet metal that holds everything. It doesn't have a top cover, no front panel. It's all optimized for airflow. It's about efficiency. How cheap can you make this thing while still having it perform reasonably? You want to optimize as much as you can around getting cost effectiveness for performance and the lifespan of this thing.
Yeah. Huh. So, okay, so it's a thing of sheet metal, right? I guess that the Zaius, how do you say it?
Zaius.
Zaius. Is it like Dr. Zaius? Like the...
Yep. We have a habit
Dr. Zaius, Dr. Zaius.
giving our server projects a lot of interesting names.
Yeah, okay. Can you give us I mean, we'll try and link whatever pictures we can, but could you give us kind of an idea as well, like what else is in there, I guess, as like a audio picture?
Inside of a Zaius machine?
Sure, yeah.
So a Zaius machine is a dual socket Power 9 server from, so those are Power 9 processors from IBM. And basically, our design there, Rackspace is also using it. It's heavily dominated by the processors and RAM. It's really about getting those two pieces deployed. Okay. So the bulk of a PCB that's, think of, 16 inches wide, maybe 20 inches deep.
And a single PCB. I remember that.
Yeah,
piece.
It's single PCB. That's insane. 2 very large processor sockets. I think there's either 16 or 32 DIMM slots and a bunch of PCIe slots. That's more or less what's there. Uh-huh. There's space to put one hard drive or an SSD as a boot device. And at the back is a hot swap blind mate power connector. In OpenRack V2, it's a 48 volt distribution system.
Okay.
And
like when you say 48 volt too, is it like a 200 amp supply, or are they all like individually for each connector has its own supply?
No, it's a giant bus in the back.
Oh, it is.
Yeah.
Oh, it is really. Oh, wow.
Yeah.
Okay. So could you give us an amperage range?
It varies on.
I really just want to hear the high end. I mean, let's be honest.
I believe the OpenRack V2 spec allows for up to a 25 kilowatt rack.
Oh my God, that's insane. That's a lot of copper, folks.
And
wow.
And that's all battery backed at the rack level too. So the intent is that you put in AC to DC rectifier shelf to feed it, and then you put a bunch of battery packs also on the bus. So the bus actually isn't exactly 48; it floats with the battery voltage.
Sure.
But all of it powers off of one shared common power infrastructure there. And
holy crap!
Then all of the 48 volt power conversion happens on the server PCB. So one of the things with Zaius is actually it does 48 volt to point of load power conversion. So the CPU core rails at 1.2 and 0.8 volts are actually done in single step 48 volt to 0.8.
Oh, seriously?
Oh yeah,
that's amazing. Isn't it like those like super high frequency converters too, or what?
So it's actually, I know Intercell makes them, and a couple of other people are now selling them publicly. They're actually finding a lot of interest in the automotive groups, but
sure, yeah,
it was a really big deal of getting those parts available because you couldn't find that before.
Yeah, right. Yeah, the silicon, like, why would they make that?
Right. And now that they do, it's actually really, it gives you a really good power conversion efficiency. Got it.
So you kind of sit up on the curve up near the 95% or whatever they love to talk about, but if you're not if it's not designed for it, you don't actually get that full conversion.
Right, and I think specifically here, it's 95 would be low, right?
Sure, yeah, of course. I know. I'm still stuck in the past here, Rick. Sorry.
It's just when you're thinking about these designs, if it's a 2 kilowatt server design,
that's a good point. Yep.
The CPU and memory is considerable on these.
Yeah.
So yeah, it's really optimized around getting the CPU and RAM deployed. There are usually other server designs that are more about just bulk loading disks into the rack and making those accessible to the network. And those often are deployed as 2 separate solutions.
Got it. Okay. Interesting. So, let's, I mean, we got to get there eventually. I mean, you already mentioned it with the efficiency side. So how the hell do you get all that heat out? Because This is when you and I were talking about you coming on the show too. I said, this is where electronics people should actually learn thermodynamics. It's like, okay, we're moving some heat here, folks. So how the hell do you get all that heat out?
Yeah, there's a lot of different approaches. If you walk into a normal colo environment, colocation environment, you would see 1U servers with usually a front-to-back airflow. So they've got fans to draw air in from the front of the chassis and blow it over all the components and blow it out the back. And they will do thermal control where they have a management processor that monitors the temperatures of key components and locations inside the chassis, and usually break up the actual airflow into zones inside the chassis.
Okay. So like the processor would be the hottest zone kind of thing, or what?
Well, it's more, if you think of a channel of air going from front to back, you might put baffles in to separate that. So the processors are going to be hot, but they're going to have a lot of airflow, whereas the DIMMs might be less hot and need less airflow. So you want to be able to control those two zones independently in terms of fan speeds.
Got it.
And overall airflow.
Yep.
Because the more you spin the fan, the more power you're burning in your fans.
And that becomes a consideration too, because there's just so many fans, or what?
Yep.
Wow. So it's about efficiency of electricity to CFMs, or what?
Yeah, I mean, it's a factor. You have to consider how much electricity you're burning in actually creating airflow.
Everything not processing bits is overhead, huh?
Right. And there's the industry measure for that. It's called PUE, and it's basically a factor of energy consumed over energy used for actual IT load, right?
So
like doing
POE?
PUE.
PUE. Okay. Interesting. Okay.
Yeah, power usage effectiveness. And it's a pretty standard term at this point in the industry, but it was not a big deal until a decade ago.
Mm-hmm.
And the goal is to get to 1.0, right? If you could do 1.0, it means literally you're spending no energy on anything other than running the actual machine to do work.
Yeah, right.
But yeah, everything from, spinning the fans to pumping water to cooling water to whatever you need to do to actually do the thermal management, keep the lights on, etc., falls into that.
Well, and you said that the old way of doing it was moving air front to back. So does that allude to something else happening these days, or what? Well,
it's more that you move out from the mindset of a freestanding rack pulling air out in through the front and shooting out of the back with open space on either side. That would be a traditional colo, right? Just like a rack sitting in the middle of a room.
Yep.
A lot of colos have moved to a hot aisle, cold aisle scenario, where basically think of putting a baffle or a divider over the middle of the rack, cutting it into a front section and a back section. Uh-huh. So the front section is where you pump in your air-conditioned air, your cool air. So that's your cold aisle. Yep. And the machine then pulls the cold air through the front, pushes it out the back, and goes into the hot aisle. And then that you put your air conditioning system so it draws air from the hot aisle and pushes it back into the cold aisle.
Right. It's like a heat exchanger, except the heat exchangers also happens to be processing bits.
Right.
Yeah.
So that was a fairly common approach. And then when you actually moving into extremely high workloads, you start moving the cooling infrastructure closer. So if I was, using a normal chiller setup, and I was taking that hot aisle air and having to blow it out to a mechanical equipment on the roof and then pump it all the way back, that's a really big cycle.
Right.
To move the air around.
Yep, exactly. And then you lose efficiency as you get it, or you blow it over the coils, and then it comes back down. Entropy just increases the heat of that air, right?
Right. So instead, you can imagine using chilled water, where you put your chiller to cool down the water supply somewhere convenient, and then you run that chilled water up to near the rack and put the heat exchanger there. So the air to water exchange happens very close to your actual heat production.
So it's like a radiator type thing,
yeah.
Okay.
It's a heat exchanger that's going from air, the hot air coming out of the server. You're transferring the heat through the heat exchanger into water, chilled water, and then the water carries that heat out to a chiller that actually extracts that heat out somewhere else.
Big ass thing, huh?
Yeah.
Big ass compressor. Yeah.
Yeah, and so that's you hit on the number two concern in deploying systems is the overall how much heat can I actually take out of that space. Number one is usually how much power can I get into that space.
So you mean like power delivery over that 48 volt thing, or what?
Right. Well, actually, and down into the rack. Even if I'm running, 208 3-phase into the rack, there's still a limit as to how much power I can actually deal with inside that rack. What's the size of all of the wiring?
Size of the inverter, or the size of the rectifier, size of the or the copper in the wiring, stuff like that.
Right. So and then it turns into, all of that power that you can deliver in has to turn into heat, which then you have to deal with the cooling side. And the third one is actually the weight of the equipment. Can the floor actually support it?
Holy crap. Right, and you're trying to keep costs down on the infrastructure level as well, so you don't want to have to make some like triple reinforced steel beam thingy.
Exactly.
Yeah, right.
Yeah.
I remember the infrastructure underneath a semiconductor facility, like, man, that is some intense shit, and I can imagine that you don't want to have to do that, right? Like especially if you're trying to like rubber stamp these things all over the country or different countries as well, right?
Yeah. I mean, ideally in a data center application, you want things to be really inexpensive. So if I can just have a simple poured concrete floor, that's great. Mm-hmm. But that means I can't use a raised floor system to run all my cooling pipes and all that kind of stuff. So
wires and
how does that change, and where does all that equipment go?
Well, okay. So you had mentioned a connector, and I didn't write it down. So you said the 48 volt rail has some kind of standardized connector. Is that right?
It does. It's actually it would be a part number, but it's a blind mate connector. It's
blind mate, like you could plug in without looking, kind of thing. Like
exactly.
It self-aligns.
It's designed that you can take a tray, which is effectively a machine, and slide it into a slot, and it just blind mates directly into the power rail. And then
nice.
And then the hot swap connector or hot swap controller powers up and brings the machine online.
Right. And for those who don't know, could you explain what a hot swap controller is?
So hot swap controller, you essentially, if you've ever plugged in a charger or something with a high capacitive load into a wall outlet and you see the sparks fly, if you put an immediate load onto a power delivery system, you can have a lot of problems of like pulling the rails down or arcing or whatever. So a hot swap controller basically just monitors the power coming in on that connector, waits for it to stabilize, and then allows the rest of the system to start powering on.
Yep, those are great. And actually, I didn't realize. So when I went to an industrial company, I didn't realize they used to do that mechanically, where they would just they would move so it would be like a card edge thing, and then the card edge the finger on the card edge, quote air quotes, would just be one would be a little bit shorter, and so that would contact second kind of thing.
Right.
But that doesn't quite do it when you're doing a ton of swapping out and stuff. So
right.
Yeah, hot swap controllers they're great little chips. I mean, they're just usually it's like a P channel FET and a little like a like a boost converter pretty much, or not even boost converter. It's like it's just monitoring current draw. Right?
Yeah. It's something that has to decide if the power's in a good enough state. Is it okay to actually start powering it up, and maybe a soft start of some sort.
Mm-hmm. Well, that's great. That's cool. Yeah, it's really interesting too, because like as you're going through these different types of silicon and stuff like that too, I used to have sales guys walk around and tell me about these new chips, and sometimes I just didn't know what they were for either, and obviously some of it I can assume that this is a huge part of the industry as well, like just a ton of silicon going towards this stuff.
Yeah, there's a whole bunch of specialized components that go into these servers and into the racks and all sorts of places. There's any part of the system that you look at, there is a small sub-problem that has a specific solution that you need to find a way to solve it.
Mm-hmm. Yep. So another thing you had kind of alluded to is, I guess we were talking about power wiring, and that's a huge concern. But what about the actual networking side as well? So, like, is it all Ethernet? Are there non-standard things that I wouldn't expect connecting between boxes, or how does that work?
A lot of it is pretty standard at this point. A lot of it is really moving into the really high bandwidth stuff. So not things that you would find at your average, going to Fry's or at your desk type thing, but 10 gigabit or higher switches and things like that.
But it is still Ethernet based. It's still squeezing it down to a single pipe instead of doing like some monster paralleled connector or something like that.
Well, I mean, it depends on how you look at it. Like 40 gigabit connectors with QSFP is sort of a parallel scheme over it because it's really designed to run over multi-wave fiber and yada, yada, yada.
Oh, really? Wait,
it's basically, as you get into these really high bandwidths, you're trying to figure out techniques to
squeeze more stuff, right,
through a single fiber.
Like when we talked to Dave, it's going over the transatlantic fiber cable thingies, right? And it's packing in as many bits as it can because there's only so many fibers going under the ocean.
Right.
So,
yeah.
But it is fiber optic though. It's not like Cat5, like copper.
It's changed over time. It originally was a lot of copper, and as we move from 1 gig to 10 gig to 40 gig to 100 gig, you just get to a point where fiber makes more sense everywhere.
Okay. And then, but like connector wise as well, like is it like
it's all standard stuff. I mean, SFP and QSFP modules on with fiber connections. Okay. It's not going to be a Cat5 because that would be copper.
Yeah. Right. Okay. I guess I don't know any fiber connector names, so that's really what I'm getting at. So yeah, I mean, like I have no need for that ever. So that's cool though. And so okay, so then what about like hooking banks together, machines together, all these things? Like, do they all go back to switches? Are they going machine to machine, like daisy chaining? How does that work then? Well,
the goal, again, as we touched on before, is moving data between machines as fast as you can, right? Especially at a cluster level, which is sort of, think of it as roughly a room of machines as a cluster.
Okay.
So if I want to have a fully connected mesh between all of those, that would be interesting. And so that's not particularly practical, but what you really want to do is build a networking topology within the cluster that lets you have as much bandwidth as you possibly can get from any to any.
Okay, so yeah. You're saying because if they have to all go up to some master machine and then go back down, then that's a longer traverse path rather than going.
Well, you have a fan-in problem. If I have 1,000 machines that all have 10 gig connections and they're all saturating it, then I have 1,000 times 10 gig data coming into that central point.
Okay. So that would be like a hub and spoke model versus mesh would be like everything's connected to everything. Is that kind of the idea?
Yeah, and so you can think of it as a whole bunch of machines connected to a rack switch. And they are all, single connections from the machine to the switch. And then at that top of rack switch would actually have maybe 16 connections that fan out into different switches that make up part of the cluster fabric. And it will, and because it has all these different paths it can possibly go, it will spray that traffic across all of the different ports. So you're actually balancing over all of the available links on the network.
So what are you guys like starting to replicate like neural connections as well? Like, is it like starting to look like that of like a really big brain or how does that?
I don't think so. I mean, no? I'm not.
Just tell us when it's going to happen, man. Just give me like a rough year when I should expect to, lock myself in.
AI has not replaced my job yet, so
I don't even know. I'm still trying to figure out what the hell you do, man. That's crazy.
Mostly, I go to events and write firmware.
Yeah, that's okay. Well, this is that's crazy about just because there's so much data too. So okay, and I also wanted to get, because this is an interesting segue as well. So what's controlling all this stuff? So you mentioned OSs at one point, at like a machine level, but then there must be another layer on top of that that's kind of like scheduling, telling it where to go or giving it addresses, or how does all that work?
Yeah, there's a lot of different solutions for that. But essentially, you think of it as, at the machine level, you probably have a management controller that it's basically like a lights out management type system. So you have a dedicated way of talking to the machine to do power control, monitor the system health, collect inventory information, etc. And then you would boot an OS on the host machine that is often Linux, but doesn't have to be, that deals with making that machine useful and participating in the network. And then you'd run some software on that OS that connects it into a cluster level scheduling system of some form. Kubernetes is one approach. The OpenStack software stack has an approach to that. There's another one is called MOS, Metal as a Service. That's by the Canonical folks. And basically the whole idea is the machine has to advertise what resources it has available to the cluster scheduler. And then that gives an endpoint for people to actually either request a machine or to request specific resources. And there's different usage models. Like the MOS model is, I want to be allocated a machine. I don't care which one it is, just give me a machine and install the OS I want on it. Whereas Kubernetes is more, I want you to run my Docker container and I don't really care where it gets run. But there are all these different models, and it's still an evolving space where you might run multiple models in the same cluster and divide up the machines, or they might build on top of each other. You might have it be that Kubernetes is using MOS to request machines as necessary.
Interesting.
Or,
Okay, so could we maybe take a journey as a packet of data? I mean, I'm trying to put all this stuff together. I know this is in your head, but man, this is a whole. I really feeling for people like I'm at least I run virtual servers sometimes, and so I'm a little bit in there, but not even close at this level.
And I was expecting to go the other direction and talk more about hardware.
I mean, we could do that. We still can talk about that more too, but this is just there's so much vertical space between I enter a URL and then it gets to silicon and it bounces something back to me. You know what I mean? There's a lot of layers in there.
There are, and especially when you talk about an actual public cloud service, you might pass through 10 or 15 machines before it actually ends up at your application.
Yeah. And that's the other thing too, is that so all this stuff is abstracted and automated and whatever, and it's and people are deploying these services that have existed and are evolved, but now I'm trying to think about it all at once, and it's like a fire hose, right? So that's why
exactly.
It's crazy. Yeah. Okay, but the thing I'm really wondering about is at the networking level, machine to machine.
Mm-hmm.
So machine number 1 has a packet that it needs to send to machine number 2. Does it have an address that it sends it to, or how does that even work?
I mean, it looks very much like a standard network, at least as far as the machine's perspective.
Okay.
Often what you see is a rack is assigned a subnet, and it's treated like a layer 2 switching domain, which is very similar to anybody's home network.
Okay.
And you might
machines behind a firewall, like a switch in your house.
Exactly. And so you would have an address per machine, and they're all on the same subnet. They can all talk to each other directly, and that works for a rack of machines. And a rack can fit 72 machines, no problem.
Right. So it's just about keeping which 192.168.0.0 you're actually talking to and which rack.
Right, right.
Keeping those straight.
Right. And that's really a management problem. And people build custom systems for tracking which host name is which IP address and serial number and all that kind of stuff.
Got it. Okay. All right. So then that's interesting, because then that kind of does remove, at least it's a little bit standardized. It's just at a lower level than I'm ever used to interacting with.
Right. And then as you're leaving the rack, then things get more interesting you're moving into a layer 3 switched system usually, so you're actually going through many different switch chassis, and it's forwarding it along based upon the IP address rather than MAC addresses. And so that's where you're connecting all of these layer 2 subnets together.
Got it. I never even knew what subnets were for. So that's way beyond my pay grade already. So, okay. Yeah. Well, let's dive way back down to the silicon then, because that's, I think, what you're talking about, like the silicon stuff and
wherever you want to go. I mean, like I said, I do a lot with Open Compute, and I know, when I brought Zeus in, everybody was pretty shocked that, you can actually go get server designs that are, all the schematics are available, all of the board layout files are available. There are fully documented server designs actually on GitHub now.
Yeah, and we will link to them. I was actually really blown away by that. Yeah, the whole Zeus thing. So, what else is? I mean, so I guess some of that is kind of organizational too, like what's coming, what's in the pipeline. But what else should we know about the Zeus? I mean, maybe from firmware's perspective as well, because that's what you've done in the past. What is the firmware on there? I don't even know.
Well, so my team deals with the management controllers primarily, which in this case we run a software stack called OpenBMC. That's a Linux distribution. That was the specific version we're using was started by IBM, and we work with them as an open source community to basically build. If you've ever had a server that has an IPMI connection or those lights out management processors on them, that's exactly what this is. And so we're just re-implementing that as a standard Linux distribution.
Could you define lights out management? Does that just mean like a headless system, no displays, no interfaces?
And nobody physically in the presence of the machine. I should be able to power the machine, or turn power on to the machine remotely.
Oh, okay. Interesting. Okay.
Yeah.
And so this is kind of supervising all, it's looking at everything on board. And is it also scheduling stuff? You said a management system. So is it?
No, this is actually so these they're chassis managers. They're basically a processor whose sole purpose is to make sure the hardware is functional and to control the power state. You know, I can turn the power on, turn it off. I can restart the machine. I can collect the serial numbers of each component.
Cool.
I can pull the temp sensors and things like that. And it provides a way to do that even when the host processor is actually turned off.
So is that like a separate connection then, or how does that actually do with that?
Often it is a separate connection. There's usually a second Ethernet jack on the machines. There's actually a newer standard called NCSI that is a way to connect that Ethernet interface into a separate NIC and have a single connection going off to the rack.
Oh, okay, cool.
Yeah.
Network interface controller, is that NIC?
Yeah.
Okay.
Yep.
Wow. Okay, that's cool. So who's watching the Watchmen?
Who's watching the Watchmen?
Yeah, like how do you know if your process the open BMC's dead?
Well, I mean, you see that remotely. I mean, that's where you have a cluster system that knows that there's supposed to be these management controllers out there, and it's asking them status of, are you alive? Are you powered on? What temperatures are you seeing right now on all the components?
But what about like if all your temp stuff's out of spec? I mean, like how do you know? Or maybe it's not as
it's really
accuracy isn't necessary or what?
Well, think of it as I have a cluster of machines, so I can use that cluster of machines to run software that monitors the cluster of machines.
Hey, bro. Yeah, got it. Okay.
Yeah.
But yeah. Okay. How important is accuracy? I suppose this is a general question too.
It depends on what you're dealing with. I mean, temperatures can be quite important. Like you're trying to keep control at maybe a degree Celsius.
Okay.
What you're really looking for is cases where things are out of thermal spec. You want to know when things are going to start exhibiting problems.
So like SPC, like trending type stuff, or what?
Really, you're looking at the manufacturer probably has a max temp spec for their part for operational range, and you're trying to compare to that to see how close am I to that actual top of spec margin.
Got it. Okay.
Yeah.
Okay.
But you might also be looking for things like, is the fan speed seem plausible, or is it zero?
Right. Yeah. Right.
Yeah.
Yep.
A lot of the health monitoring aspects are, how do I know if a problem has occurred or a problem will occur?
Right. And then who is... So you mentioned the servers are watching the specs kind of thing, or it's reporting back up to some supervisor somewhere, which might be running on the same server or whatever, right? But how does that end up impacting other things then? Like, so is it just like go, no go? Like if it's too hot, you just say shut it down and don't use this machine?
Yeah, a lot of it is very heavy-handed that way. If we notice a problem, you want to stop using it, right? And shut the machine off and have somebody come fix it.
Okay.
It depends on exactly what the failure is. If I go to a temp spec, maybe what I need to do is just turn the fans up.
Okay. Yeah, right.
You know, another option is maybe I just need to tell the OS, by the way, I'm going to throttle your scheduling so that you use less power.
Okay. And so it is dynamic like that then too. It says, so you talk up to the scheduler up top and it says, you say machine whatever is a little underperforming, don't send as many jobs, that kind of thing.
It's more local than that for that rapid response problem. You know, if I'm actually in a thermal situation, that's usually more dealt with at a single machine level. So it would be the host processor software would be talking to the management processor. It would notice when it's getting out of spec and it would go ahead and take action. And then the higher level software would get a notice that says, by the way, I got to slow things down a little bit.
Got it. It's like a flag system kind of thing.
Yeah.
Okay.
But other issues, like if I see a hard drive experience a read failure, that's something where I'm just going to stop using the disk. And I'm going to notify the job scheduler system, hey, this disk needs to be replaced. Figure out when you should do that.
Okay. Interesting. So how does all this stuff interact then at like a community? Because I have to imagine that this is So you've got all these deployments. You said hyperscale is 50,000 plus units, whatever, out in the world, and probably many more. But then, I mean, hardware evolves, so there's different revs of each thing. Is there a standard, even just for how it's talking up to the scheduler, saying like, oh, this temperature's too hot, don't use this machine? Is that like a standard API, or how does it actually interface between these machines at a programmatic level?
Well, so this is a lot of what my current work is around. Essentially, the standards for system health monitoring or remote management functions, the common standard is IPMI. It's a standard that was created by Intel back in the late 90s. It's still very commonly used. It's controlled by the DMTF now. And it's okay, but it really doesn't address some of the concerns that you have when you're dealing at these larger scales. So, for example, the way it models the system, it really tells you things like there are temp sensors, but it doesn't tie those temp sensors to what components they affect.
Oh, okay. Yeah, right. It just says in box 1, there is a temperature of 75 degrees or whatever it is.
Well, it may have multiple temp sensors, and it might say CPU 0 is this temp. But
okay, like I can monitor on the computer I'm talking on now, right? It can
exactly.
do that too. Yeah.
But I have to know what CPU 0 is. And if I'm dealing with thermal problems, I have to know where in the chassis that is to build an accurate fan model. And there's all these different caveats to how IPMI exposes data. So a lot of the hyperscalers have actually developed their own protocols and own mechanisms for exporting this data off of the machines and into that cluster level. And a lot of it comes down to, I have many generations of hardware. I need a common way of viewing that information so that these higher level systems don't have to care about every individual generation.
Right. Yeah, exactly. You would never want to expose that, but you still need, but if there's no, quote unquote standard, then yeah, how do you actually, you still need to transmit that information somehow. So
right. So a lot of my work is, well, now that we've all done that individually and come up with these standards, we're trying to figure out how to share. And we're doing pretty well at sharing at the hardware level. If I look, Microsoft makes their Project Olympus motherboards, and they're available through Open Compute. And I can buy one of those, and I can figure out how to adapt that and stick it into a rack at my work. But then when I look at the interfaces of how to integrate that into higher level management systems, I am missing a lot of detail. I would basically have to do all that work from scratch because it's all custom.
So like go write new firmware that works with your system?
Well, I mean, they have firmware that probably already written for that system, but I at least have to go in and write an implementation of the protocol that I use to talk to my cluster level services.
Got it.
And a lot of that's probably describing the hardware to those higher level systems. This PCIe lane and this I2C bus are on the same physical PCI connector.
Right.
I need to know that in order to know where all the sensors are and what devices I'm talking to trace down error information to individual components.
Yeah. Is there like a grid system or anything like that where it's like,
no.
B4, you've sunk my I2C bus?
This is a Wild West situation right now. So it's something that I aspire to build more in that space of developing standards there, trying to figure out how to actually move that to a model where the hardware designers can actually just specify this is how the hardware layout occurs at a logical level and a physical level, so that the software can just examine the hardware and say, maybe it's putting things in the ACPI tables or other things in the system firmware that say this is how all that stuff is connected. But it doesn't exist there today.
If you do a grid system, can you call it the GAML system? Is that we're agreed on that? Is that cool?
I will take that under advisement.
Okay, great. That's all I really want. I mean, that's fine. Yeah.
You just want your name somewhere in the history of computing.
Exactly, yeah. Right. And then at some point it'll be cursed out. That damn GAML system. Yeah. So I mean, does it all flow up through the Open Compute project then? Like, how do you actually, I mean, you said you can buy this Project Olympus, but like, how do you interface? Is it just like you email Bob at Microsoft or whatever, like, the people there, or how does that work?
So the Open Compute group has a structure of, there are members as well as new products. So there's implementations of these standards. So like Project Olympus is a set of standards. They have one for the motherboard form factor, for example, and where connectors should be and things like that. And then there are implementations of that where they have an Intel-based server and they might have an AMD-based server and a Cavium-based server that are specific implementations of that.
Okay.
Then they have other members that are called solutions providers that work with the ODMs to actually manufacture the equipment and sell it to end users. So you would actually go to an ODM like Penguin Computing or Horizon Solutions to actually order the equipment.
Okay.
But the intent is that we're all sharing the designs.
I was going to say, plebs like me could go and do that if I had enough cash on hand?
Yeah. Yeah, I mean, if you go somewhere here, on the opencompute.org website, there's a marketplace link. And it has a link to, it has a list of all the different types of machines and who you can order them from. So if you're a large enough volume, you can go directly order that from an ODM. Be prepared to buy 40,000 of them. But if I go to Penguin Computing, I can probably buy them in much smaller units. But it's also
but higher cost per unit then, right?
Yeah, exactly.
Yeah.
Yep.
Wow. This is insane stuff. Like this kind of scale, it's a good name, Hyperscale. That's definitely a good name. But damn, that's crazy.
Like the second thing I see on the list here is actually from HP Enterprise, and it's a 48 port 10 gig switch with 6 40 gig ports, an x86 CPU. That's a standard rack switch for us.
Okay. I don't have any reference point, I guess.
Well, how many people are going to have 48 10 gig ports on a switch?
Yeah, it's true. That's a good point. Sometimes I plug a Raspberry Pi into mine at home, so pretty much the same thing.
Yeah.
Wow. Yeah.
But the cool part about a lot of these, when you look at it, they'll have the links to the actual specifications, and you can download a lot of the information, the schematics, the board layouts, and that kind of information.
And so, what is the layout program du jour? Is it all Mentor?
It varies from company to company, and ODM to ODM. Often, you see a lot of Cadence.
Okay. Cool. Is it worthwhile for people? I guess you can go. That means people listening to the show could go and open it up with one of the viewers. Usually, they have free viewers, right? You can go and look at it and see how they do the crazy DDR4 layouts and stuff like that, right?
Yeah. Part of the challenge that I've faced is, we provide these server designs to the public. They are available. What can people actually do with them?
Yeah, now what?
Right?
Well, first off, you go and you buy a Cadence license for 20 grand
and then you open a 400-page schematic, and then you then you look at a 20-layer board layout, and
right.
There's a big skills gap there that honestly I don't know how to fill that in. I've talked with a variety of folks who understand that the knowledge of building this scale of design is very niche and very isolated to these very large companies, and they're trying to figure out how to make a model out of bringing that more to the masses.
I guess this is kind of an open source question in the first place, right? It's just that how many people even open the schematic, right? Or even open the layout,
right?
In any case of it. But I think at the base of it, the fact that it's the people that really need it are already working together, it seems like. So that's a great start in terms of building out alliances and standards and stuff like that. The rest is just kind of nice to have.
Well, and a lot of this, as the standards show up in the Open Compute group, often those become, once they've stabilized a little bit there and gotten a little bit of runtime, they seem to get pushed into the larger industry standards. So I know there's some work on hard drive firmware and hard drive features where the T11 and T13 groups, T10 and T13, the ATA and SCSI standards groups have already said, whatever you guys decide that you're going to do in the Open Compute world, we'll use that as the preview of the standardization process. So when it comes into ours to actually put into the formal specs for hard drive manufacturers and storage controllers.
Oh, that's great. Yeah.
It's been pre-vetted as this is probably only going to make sense to data
close.
centers.
Yeah. Right. But why not standardize on it, right? At
Right,
that point.
exactly.
Yeah. Wow. Okay, well, let's talk a little bit about data centers, because this is another thing you sent me. You sent me there's a Google seems to have a good page about their data center. I was just watching a 360 tour inside there, stuff like that.
Mm-hmm.
What should people expect to see when they if you went into a data center? I guess you like I said, you can go and watch this 360 video, so that's very interesting. But like, is it just all pipes and I don't know?
Yeah.
How much does that stuff impact your work, I suppose?
Actually, quite a bit. One of the things with the hyperscale is we design the machines, we have the machines manufactured, we have the machines deployed into data centers, we see them through their full life cycle until we decide they're no longer worthwhile keeping, and then we deal with the end of life and destruction and recycling aspects of it. So the time where it lives in the data center, we have to understand how people interact with the machines there and what that environment is like. So a lot of it is really just putting ourselves in the shoe of these are who we make the machines for. Are the people who have to actually go walk out on the floor and touch each machine. But for the most part, they are very industrial settings. As you'll see in the pictures, if you go to the google.com/data centers, it's a lot of, in our case, colorful pipes.
Yes, those are nice. Those are really nice.
But that's like the cooling plants and things like that. And then
all this like heat exchanger stuff, all the stuff like the subfloor stuff, that actually was very reminiscent of below a fab as well. I mean, maybe more individual gas pipes and stuff, but yeah.
And then the actual data center floor is just row after row after row of racks. I mean, it's machines as far as the eye can see. To give a sense of scale, room can easily be 300 yards by 100 yards, easily.
Yards, huh? Wow, we're really going American on this one.
Yeah,
19-inch racks and 300 yards.
Well,
I know you always say that though because they always give it in the 3-football fields, right?
Yeah,
that's what they love talking about.
Pretty much.
Yep. I used to work in a 9-football field situation.
But to help out our non-American friends, let's see. So, think about 300 meters by 100 meters as a building.
Yeah, it's pretty. I mean, it's pretty close.
It's
right?
pretty close.
Like
yeah.
But it's
okay.
So
they're massive, and so
yeah.
you end up in these situations of even locating a machine inside of a data center is a problem.
Really? Oh, okay. So like when the scheduler says machine whatever ABC 123 is down.
Yeah.
Now what?
Where is it?
Yeah.
And I have lots of fun stories about that. I mean, there's just the problem of you're in a closed building, so GPS isn't going to work for you. You're talking about really tight locations anyway.
Right, and probably highly dynamic as well.
Right,
of like
high RF emissions just from the sheer amount of machines around you. Lots of metal and things. So most locationing systems don't work very well. Maps need to be very dynamic because equipment's constantly being moved around.
Yeah. Right.
So it's very common to get lost into a data center. Most of them have incorrect signs. Sometimes you're just wandering down the aisle looking, going, okay, so I'm in the, I'm near this section of machines. It should be the next section. Oh, wait, it's not there. And they've tried different things. Maybe we paint an artificial starscape with paintballs on the ceiling and then use a camera and constellation tracking software to figure out where I am.
Oh, that's a cool idea. I like that.
There's
QR code, stuff like that.
Yeah,
like
I mean,
AR
it's
stuff.
just trying to find ways of actually being able to navigate the facility is a challenge.
Could you just make like little robot carts that just take you where it's supposed to go?
Wouldn't that be cool?
Wait, is that yes? Are you going to do that? You should do that. You can call them gamel carts. I'm sorry. I don't really propose that you call anything.
But then they'll get confused with the gamel grids and.
Yeah, right.
Yeah. So that's one issue. Another issue is just the sheer quantity of parts that you need to have on hand to repair machines.
Yeah, like a stock room kind of thing.
Oh yeah.
Wow. I'm paused at like sorry, I don't mean to be. I'm staring at this 360 video, and this is actually a great use of 360 video, which normally I'm like, man, whatever. But like I'm keyed in on 445 on this video that I'll link in, but like it's just like rows. I mean, it looks like the weirdest looking library ever, but man, it just keeps going. Perspective runs out basically.
Yeah. I mean, it really is.
What
that
the hell
way.
is on all these things? This is my emails somewhere on these things, right?
Yeah.
Oh,
At least
man.
one copy of it.
Yeah, right. Man, that is nuts. There's so... I mean, how many servers to humans are there? I mean, like, is there a measure of that?
I never think about it that way. Actually, I had a coworker who asked us to think about it in terms of people per megawatt deployed.
Yeah, that's okay. I was going to ask about power stuff too, so keep going. Sorry.
Well, it's just when you think about your operational load, it's really how many people do you need to maintain a certain number of megawatts of deployed capacity of machines, and that was really the optimization metric that we were trying to think of. How can you use the machines and software and other things to reduce the number of times a human has to touch things?
Yeah. Right, because that's what a true dark, what do you call it, like a lights out facility. Mm-hmm. This does not seem lights out because there's just so much maintenance to be done. But like that was always the promise of like robotics facilities as well. Is like, oh, you just turn off the lights and it just keeps going. Right. That's the idea.
Right.
But damn, I mean, so like that 300 by 100 meter facility, how many rough people would you even need? I mean, is it like?
It could be as small as 100. I mean, it depends.
It's still a lot of people.
It's still a lot of people, but
yeah.
It depends on exactly what is being done there and how often things are turning over.
Sure. Like something like super high powered or specialized then.
Well, and don't forget, for any site you have, you're going to have the needs of physical security and HR and all the associated things. So it builds out staff a little bit quickly.
Yeah. Well, more reasons for robots, I suppose, but damn. Well, okay, so I want to ask about power as well. So a data center's in the megawatt range or multiple megawatts, gigawatts? What is, I don't actually know.
Can't really give a specific numbers.
That's okay.
Yeah,
sorry.
No, it's a fair question. I mean, certainly thinking in megawatts is reasonable. I would say anybody who's dealing in large enterprise or hyperscale would also be in that range.
Okay.
Yeah.
I mean, because the reason I ask is because, one of the things right on the data center page is talking about renewable energy, right? Mm-hmm. And so, like, just talking about, like, cooling is one thing, right? So, again, like you said, you're in the 90s for efficiencies, but I assume that overall efficiency of a data center is probably not more than, 90%, power into actual, well, I guess it doesn't all get turned into heat, right? But there's a lot of heat coming out of there. Mm-hmm. And so you think about, like, not only do you, if you have a 1 megawatt facility and it's 90% efficient, then you still got 100 kilowatts of heat that you got to get out of there then too. So like talking about just the infrastructure stuff of powering the facility and then cooling it for whatever the waste heat is. Mm-hmm. So that number seems monstrous.
Yeah.
Right.
Yeah. I mean, when choosing data center locations, you got to think about, I need a place that has a lot of space. I need a lot of power. I need a lot of networking bandwidth.
Oh, yeah, right. Yeah. Backbone upon backbone, huh?
Right. And those become your selection criteria. It's not.
Yeah, but then they like end up in like Iowa. I don't get that. Like sometimes I've seen like some of it seems some of them are really remote, I don't get that.
Well,
sometimes.
Often that can just be the case of there's a lot of power available there. Maybe it was an old manufacturing area that had a lot of power infrastructure built up, and that is no longer being utilized to full capacity.
Interesting. Okay. Yeah, that's cool. And I guess that's the other really interesting thing about data centers in general is that it all is down to an equation. It's like how much processing can you do per dollar, right? That's per dollar, I guess. Yeah.
Yeah.
And it's like the whole like people that are like Bitcoin miners talk about that all the time too, where they're like, how much processing can I do? How much is it going to cost me in electricity and resources to get one Bitcoin, right? It's like,
right.
That's a similar, much smaller scale kind of thing.
Right. Yeah, it's a constant question, and it's a lot of how we set up our decision-making process is around which choice gets us a better return on the most compute power available to us per dollar.
Yeah. Huh. So, well, okay, I was going to say, I was going to ask a question that I don't think I'm allowed to ask, but I would have to assume, I'm just going to make a statement here then, I guess. I would have to assume that you, if I was going to, if I was going to build a data center, there would be times where I would start to do more and more custom things just because the scale makes sense. So like even to the point of custom silicon, custom capacitors, custom connectors, all these things. I mean, obviously some of that's already in the open compute, but you're trying to get other people to make it, but there's probably a lot of scale decisions that are based on that, right? You start to look at like tall poles and say, well, let's get this cost down, and how do we do that?
So build versus buy is always a consideration.
Okay.
Because we do have people, we have design people. We have people who can design and make equipment.
Right. Google hires some talent. Facebook hires some talent. Yes, they pay a lot of people.
So, but it becomes a question of, is that an effective use of money? So if the industry is caught up enough and delivering something that's good enough for our purposes, then go ahead and use it.
So it's more like it's when you want to do something new that you can't yet do. That's more of a reason to dive into that thing.
Yeah. Okay. Or you think you can do it in a significantly better way. And there's always trade-offs. Maybe it's time, as you see in open compute, a lot of the ideas are being shared where it was proprietary knowledge before, but it's being pushed into standardization because that customization starts to lock you out from buying the commodities now.
Right. Yep.
So it's
and I always talk to students about that when I'm teaching electronics. It's like, figure out what a lot of people are using. You're going to find cheaper parts, right? I mean, if you get locked into that one part, it might be that one spec that you really need, but really make sure you need it first, right?
Exactly.
Yeah. Yep. And I'm sure that at the scale you're talking about here, too, you probably have chip vendors falling over themselves to offer new solutions because they've got people internally that are doing that stuff as like, well, that 48 volt to 0.8 volt converter. That's really fun, actually. I like that. But like, they're out trying to prospect the next chip that can solve these things, right? So.
Well, everybody wants to sell to you when you're a large company. I mean, that's just
it's true.
The nature.
The belle of the ball.
Whether it makes sense for you to buy
very,
from
very rich.
Whether it makes sense for you to buy from them is a different question.
Yeah, right. Yeah, I can imagine there's times when it's security issues or other stuff like that as well. Mm-hmm. So, isn't it kind of nuts that all this stuff goes... I mean, like, the whole thing is that, like, when you really think about, like, a single bit traveling from the URL or from my computer through all the stuff, and then of course, like, this makes sense, but, like, the fact that it's going down to a server and touching down on a piece of silicon and actually flipping a transistor is signifying that, and then it goes all the way back up through the stack. Mm-hmm. Man, there's a lot of stuff in there, isn't there?
There is.
Yeah.
Yeah, there's a lot of people and a lot of engineering time invested in that.
Yeah, that's crazy. And so you mentioned like it started to change 10 years ago. Why was that? What was that shift? You were saying like some of these things had started to change about 10 years ago.
Well, I mean, it's a rough guess as to exactly when that happened. I think what you look at was there was a time where internet service providers or internet service companies like Google and Yahoo and those folks, they had a lot of machines and they were hitting scalability challenges. But the mindset of moving towards completely custom data centers where you control and try to optimize for efficiency was just new thought process.
And so what did they used to? They used to then rent other people's data centers at that point? Is that kind of the idea? Or what?
Yeah. I mean, everybody, when you're small, you do colocation. And eventually you get to the point where you're buying half a building, and that's where you start having to question, how much space do I need to buy? And should I just be building my own buildings? And
Right. And also projecting out and saying, well, I could keep doing this, but maybe it's 6 months from now, it's a different story, right?
Right. And then you hit maybe 5 or 6 buildings and you go, well, if I'm building 5 or 6 buildings and I know that I'm growing at this rate, can I sustain that?
Right.
Or do I need to go back and figure out how to utilize those existing buildings more effectively? So there's just been a progression over time. As the deployments get larger and larger, you start asking different questions.
Yeah. Okay. And actually, that's another good question too. Are there upper limits on scale of data centers as well? Like, I mean, I guess you mentioned the floor in terms of like weight bearing and stuff like that, but is there a reason that there wouldn't be some mega scale data center?
Failure domains become an interesting problem. So as you get larger and larger and larger, if you build it as one gigantic building block, then you have to figure out what are the common failure points. Because if I take out an entire building and it is now a massive
power
building,
loss, whatever.
Yeah, natural disaster.
Earthquake.
Yeah, exactly.
Yeah, right. Yeah, flooding. Right. Yeah, exactly. That's going on now.
You have multiple buildings in different geographical regions to deal with that problem, but it's still a massive outage of equipment. So you start to question, how do I break things up to reduce the number of common failure points? How can I break it up into smaller chunks that can keep operating independently? And what's that optimal point? Where do I make that trade-off between, I would rather it be a big system that's treated as one big block by the end user versus I really want it to be these smaller chunks that can easily come and go on their own.
Is it is that even to the point where it would make more sense to have two buildings in the same town instead of one big building in the same town? Is that kind of like even to that level?
Yeah, it can be.
Okay.
Yeah.
Interesting.
Yeah, it's not uncommon to see data center campuses.
Oh, really? Okay.
Yeah.
Yeah, they do that with chip fabs too. So I keep going back to that. I know that's really all I know. That's the only thing that is at this scale that I can even think about.
Right.
So, are they all one floor? Or do any of them? One level, I suppose, not one. I know there's subfloors and subfloors and stuff.
I know that there are places. There are facilities owned by other companies that are definitely multi-floor. Some places actually try to mix office space and data centers. It just depends.
You could heat the office space in the winter, I suppose.
There's lots of different concepts, or it's just like land space might be a very high premium, so you don't actually want to completely waste it just for a one level building or something like
Montana is different than Tokyo, right?
Exactly.
by a couple steps.
Yeah, go look at a data center built in New York City, and it's going to be very different.
Yeah, right. The cost per square foot is pretty high.
Right.
Yep. Yeah. I guess there's I'm trying to not ask a question specifically about your employer, but like. How can I even ask this? I'm just wondering about the scale in terms of a team, like at a Facebook or someone else's as well. Like, how many people even work on this stuff? It seems like it's this whole. Like I said, I had no idea about all this stuff to start with, but then there's just like this whole other world of people working on this stuff.
So scale-wise, I think it varies from company to company. And I know even within Open Compute and the people I know there's different approaches. There are companies that act more in developing the specification and hiring out to an ODM to actually build all the equipment.
Sure.
There are companies that take more control of the design and do maybe joint development of schematics in a JDM type model. Or it may be that they actually do the full design and use an ODM just to do board layout and fab. So your team size can vary considerably from company to company, but you can also do a lot with very few people if you have talented people and a common purpose. If you wanted to do just servers and do that kind of deployment, the engineering teams aren't necessarily very large. It may only be 10 people actually required to build a server from getting the schematics and the overall layout. By the time you factor in supply chain and all the people to actually get it to something physical landing at a data center, of course it's hundreds of people at that point.
Yeah. Okay. Yeah, that makes sense. And I guess there's also the like Intel is going to give you reference designs and field support stuff like that as well, or whatever vendors you're using.
Exactly.
So.
And often when you're dealing with like the electrical design, you might have a lead electrical engineer dealing with the overall system design, working with an ODM who's doing a lot of the schematic and kind of rough work or more detail work, and then have more specialized EEs that focus on maybe power subsystem or maybe signal integrity that come in to help with the design and different aspects of it.
Yeah, right. Domain experts around these things. Well, I have to imagine it's still changing a lot, huh? Obviously you've seen it. The openness is an interesting change, but do you find that it's still as dynamic as it was, 5 years ago?
Oh yeah, definitely.
Or more dynamic, maybe?
Is it more dynamic? I'd say no. It's always been pretty dynamic. Especially.
I guess is this stuff scaling linearly? I don't even know how data centers scale and stuff like that too.
Boy, that's hard to characterize. I mean, the thing is that data centers are always in flux. So we've
Like as different models go in and out of vogue, kind of thing.
yeah, well, not even in and out of vogue. It's really when is the right time to remove old equipment and put new equipment in its place.
Oh, that's a great question. Yeah, yeah.
So there's always constant evaluation of, is it time to just upgrade the equipment? Is it time to build a new site? What makes the most sense at the time? And it turns over a lot. I think there's still a lot of growth going on overall from what I hear. There's definitely a lot of interest at things like Open Compute events where a lot of companies are getting into these larger and larger deployments and they're thinking about the scale out models. And when you start hearing, companies talking about, well, yeah, I'm going to deploy 30,000 machines and I want to figure out how to actually buy that. That's really interesting to hear that from lots of different companies. It's becoming a new thought process for them, and a lot of new players in the market. Whereas before it was a handful that actually dealt in that sort of quantity.
So does that mean that Hyperscale is moving up the chain even, or
yeah, I think it's everybody sliding up. The Hyperscale is getting to larger and larger deployments, and sort of as the large enterprise moves in behind that, they just keep creeping up into the space that used to be Hyperscale.
Right. Yeah, I hear this web thing is going to keep going. I don't know.
Yeah, funny that. It seems to be really useful.
Yeah, yeah.
Sometimes.
Right. We say as we talk over thousands of miles on fiber that's, yeah. Anyways, with near perfect connections.
Yeah, why didn't I do this next week when I'm actually in the Midwest?
Oh, yeah. Well, there you go. That's all right. Well, so we're like an hour and a half in, so I feel like we should start to scale it down. I feel like we're gonna have to call you back at some point, man. But what else should people know, like, off the bat? I mean, like, especially I guess the main thing would be, like, if someone's interested in getting into this stuff, what should they be thinking about or studying or what?
That's a really good question. So I think what I've heard a lot when talking to companies that make server equipment or switch equipment, these are not skills that are taught in school. It's especially when you're looking at the electrical design or even at the firmware design and things like that. The considerations that happen at server scale and especially in large deployment scale. The cluster level service is becoming more of an open field in that you can get involved in open source. But the electrical design and the firmware design is very much still, you need to go to those companies that actually do that and get involved and figure out what makes sense. A lot of them bring in or take an approach of bringing in untrained engineers or fresh out of school or have been in the industry for a while, but not in that area, and just expecting that there's going to be a learning curve. Because where are you going to get the skill of routing PCIe Gen 4?
Who's not doing that on the weekends, man? Come on.
Right. So it's not available to anybody unless you happen to be already in these spaces. So junior engineers come in and learn that on the firmware side, and I routinely hire in people that way. Now on software, it's a little bit easier to bring in more experienced people because software at a certain level, there's a general skill set around understanding complexity and problem solving that just maps in. Yeah, they have to come up to speed on the problems that are being solved, but more often than not, people can move between different software domains a little bit more easily. Right.
Domain specificity is not a pre-requirement.
Yeah, exactly. But it's also, you got to go to these big companies that actually support development of these things. If you go to your local large company, if I walked into General Electric, they're probably going to say, sorry, right? We don't actually design our own servers.
Right. Yeah. Right. Right.
But for the most part, like, I know my team constantly has a job posting available on our public job board, and I think most of these companies are the same way. It's an area where they're large enough that it's constantly available.
Is it tied to? So I know the term DevOps, but I know that's more on the networking. Well, maybe I don't know what it is, but it seems like that's tied to server stuff as well. But is that more like utilizing the servers, or are there keywords that people should look for if they're interested in getting into this field?
It does vary a lot. I would say look for data center is one. I know at Google we often talk about it as platforms, and that's a somewhat common thing.
Okay.
But that can also get really confusing because of other uses of platforms.
Sure. Everything's a platform these days.
Exactly.
A platform as a service, right?
I would say it's actually one thing that has surprised me throughout my time here is most people don't even realize these jobs are available, and I think you're hitting on something, which is they're not easy to find.
If only there was some kind of search engine.
Imagine that. And if there were terms that weren't utilized by other sections of the industry.
Well, there's that, but yeah. Okay, well that's a good start though, and I think that like server rack. I'm sure that use your Google Foo, people. You can figure it out. But that's interesting that it's out there, and I mean I'm guessing it maybe. I mean even if does Open Compute get listed in job recs these days or no?
Not so much. It's still an area where I think Open Compute's still operating as a way to exchange between the large players for the most part. I mean, individuals can be members and contribute, and they do. But there's still the heavy players, the big players are still these very large companies. I would say it's more if you think of the big cloud platforms that are out there, they're all going to have their own hardware design folks for their data centers.
Oh yeah, okay.
And then there's the ODMs behind that, which are in a similar space.
Right, but first you got to find out which ODMs are actually in this space and doing this stuff, anyways, right?
Right.
Yeah. Well, people can do some research. That'll be good. I'm sorry we didn't get to talk about cars too, because I will link in the car talk. So you had done a great talk at HDDG about ECUs, and what was it called? Something knocking, right?
I don't remember.
Oh, knock knock, add more fuel. I like that. I like that title. That was a good one. Yeah.
Yeah. Cars are definitely a hobby, and that was just a fun talk, kind of overview of the sensors that are used to do engine management.
Yeah, it was cool. Yeah, especially like the tuning stuff. That was really neat. Mm-hmm. Cool. So where can people find you online?
So I am a pretty active Twitterer, though be forewarned, I talk about things other than tech.
No.
My GitHub is moderately active. For the most part, everybody can find me via my amateur radio call sign, which is KC8APF. And basically, if you see that anywhere, that's me.
Okay, that's great. We didn't talk about any ham radio stuff either, so
yeah,
we'll have to have you back on, and you can be our resident server. We'll be like me and Dave, talking out our asses about servers and web stuff, and yeah, we just make it up as we go along, man. So this has been great. This has been really great. So thanks for sharing about this stuff, and definitely we'll link to all the Open Compute stuff and all the videos we mentioned, stuff like that.
It's been my pleasure.
All right, we'll talk soon. Thanks.
Night.